Okay, all are on mute. Okay, so yeah, thanks guys. It means a lot when somebody appreciates, and that's what keeps me motivated. Okay, and I try my best. I try to empathize with the students, what they would be feeling, and how could I make things the easiest for my students. That has always been my goal. Okay, and I always try to do that. So yep. So the recording has been started. Let us proceed now. So today we'll be talking about what is today's topic. Let me just have a look. Is it logistic regression? Okay. So today we'll be talking about logistic regression, and in a particular business case we'll be talking about logistic. So that will be default modeling. Okay. So let me open up the documents. I think you would have received the documents already, right? The problem statement. Have you received? Okay, thanks, Praveen. Okay, so you have received the documents. Let me also quickly open it up. So, oops, why is the file empty? Okay, guys, just give me 1 minute. Let me check where I have placed my documents. Okay. So I'll go on mute, search the file, and then come back. Okay. Okay, guys. Can somebody tell me what is the topic? Is it default modeling using logistic regression and SVM in Python? Is that the topic for today? That's what I see. Okay. Okay, then let me do one thing. We have 3 classes remaining, right, in Python. So let me slightly change the topics, okay? Because SVM is a slightly advanced topic. So let me have it maybe next week in our last class. Let us have SVM, okay? Let us start with the basics. So let us start with maybe linear regression to begin with. Is that okay? So in the same order that you had, I guess you studied R. Let us start in the same order because first day SVM will become too tough. So let us start with linear, then we will do logistic tomorrow, and then we will do SVMs. Okay, that would be better. Okay, I think there has been a mistake, so it should not be SVM on the first day, right? So yeah, decision tree is tomorrow. So SVM and linear regression, they are on the same day. So and decision tree is tomorrow. Sharmin, I haven't. We were just discussing which topic to start with, so you're not late. You're on time. Okay, so let me just so let us start with linear regression then. So let me just open my files. Okay, so I'm not sure if you guys have this document. Do you have this Word document with you? Okay, don't worry, I'll explain it and I'll pass it to the Imarticus folks and they will mail it to you. Okay, immediately after the class. Okay, so this is a linear regression problem. Okay, so we are starting with linear regression. Tomorrow we would be doing decision trees and SVM will be doing next week, and when we do SVM we'll include logistic as well in that. Okay, Yeah, of course, Paridhi, I'll share the documents. Okay, so let's read the problem statement then. Okay, I'm not. You guys don't have it, so I'll just read it loud. Okay, so the data that we have is from a bank. Okay, so CNB Bank deals in all kinds of car loan. Okay, so this is a bank which gives car loans. Customers first apply for loan, and after that the company validates the customer's eligibility for loan. In case the borrower doesn't pay the loan, the losses are to be incurred by the bank. Okay, so here we have a bank which has given loans to customers. Okay, and what happens when a customer doesn't pay the loan? The bank has to bear the loss, right? That's what happens. So here we'll try to find that what are the characteristics of a customer, which decide whether he is going to pay his loans or not. Okay, so there are two questions here. Okay, the first is what are the characteristics of customers which decides whether the customer will pay the loan or not. Okay, so that's a logistic problem. Okay, I hope you understand. So that's a 1 and a 0 problem. To which customers should the bank pay loans, give loans. Okay, that is the first question. It's a 1 or a 0 problem. The next question is, now let's say the bank has given loans to, let's say, 100 people. The bank has given loan to 100 customers. Now out of those 100 customers, see, all the banks, they do some kind of analysis before giving loans. Okay, but all the banks, they usually have non-performing assets. Okay, NPAs they are called. NPAs is nothing but if somebody doesn't pay the loan, he becomes an NPA, non-performing asset. Okay, so loans are kind of assets to the bank. The bank, all the banks, they earn through loans, right? That is their only earning. That is the way they earn. They give loans to customers, and the customer will basically repay the loan. He will repay the principal amount as well as some interest on the loan. And that is the source of income. That is the major source of income for all the banks. Now, after the bank has given loans to customer, a lot of customers, they default on their loans. They don't pay back their loans. Now, what are the characteristics of customers? Which characteristics of customers determines whether he will, like, whether he will default, and if he defaults, like, by how much amount will he default? When will he stop repaying his loans? Or like after how many EMIs will he stop? Let's say you took a loan of, let's say, 1 million rupees. You have repaid, let's say, 100,000 rupees, and after that you became a non-performing asset. So what was the loss the bank incurred? So 1 million minus the 100,000 that you have already paid, that would be the loss for the bank. Okay, so that is known as loss given default. Okay, in short, LGD. Okay, loss given default. That is what it is known as. So it's a jargon which is used in the finance industry. Okay, so this is known as loss given default. So what loss would the bank incur given that a customer defaults? This is what it means. Okay, in short, this is what it is. So this is what we will be trying to find. So it's a linear regression problem. Okay, it's a regression problem where the dependent variable is, what is the dependent variable? The dependent variable is by how much amount will a customer default. Okay, this is the dependent variable. So by how much amount? That amount can be 10 rupees, or it can be 100, 10,000 rupees. It can be anything, right? So this is a regression problem which can be done using linear regression. Okay. Yeah, loss. So here I'm yet to go into the data specific here. So I was just giving you the context. Okay. Now let us look at the data that we have. Okay, so here are the variables that we have. I will show you the data as well. I'll open the data in a CSV and show it to you. But here are the variables. Okay. Sharmin, okay, let me do that. Yeah. So let me share the data now itself. Which batch is this? DSP 8. Okay. So I'll share you the codes as well. Okay. Okay. So I have sent the data. So let me open up. Okay. Where were we? Okay. So we were here, right? We were discussing about the data. Okay, so what are the variables do we have? So obviously, if we are trying to find from the customer's characteristics, from the customer's attribute, whether he will default by how much amount, so we will need the customer details, right? So we have account number of the customer. Okay, so this is the account of the customer used. This is just for identification purpose. Okay, so we are not identifying customers by their name. We are identifying them by their account numbers. Okay, so each customer will have one unique account number, right? So they are being identified by their account number. Then we have the age of the customer. Okay, the age of the borrower, the range is given here, 16 to 70 years. Okay, then we have the years of experience. How much of work experience does the customer have? So working experience, it ranges from 0 to 53 years. Okay, then the number of cars that the customer has. Okay, so these are some details which the bank is trying to find. So bank is trying to find how much of wealth do the customers have. This is just one of the variables which might be a indication whether they will repay or not, or by how much amount will they default. Okay, so the range is 1 to 4 cars. Okay, then we have the gender, then whether the customer is married or he is single. Okay, and then we have the loss in thousands. So the data that we have of the customers, here all the customers are the ones who have been given a loan. Okay, we have only customers who were given loans. Okay, this is details of those customers only. So loss in thousands, now this becomes our dependent variable as we discussed earlier. So how much of loss is the bank incurring due to one particular customer? That is our dependent variable. Okay, so this is the problem statement. Let us quickly have a look at the data. So let me open the CSV file. Okay, so as we discussed, these are the variables. We don't have a lot of variables, so it's a pretty simple analysis, but the challenge will be to build a good model. We will see what are the challenges. Okay, so this is the account number as we discussed. This is just for identification purpose. Okay, then we have the age of the customer. So it starts from 16, goes all the way till 70. Then we have years of experience. So 0 to 53 years. Then we have number of cars. So 1 till 4 cars. So there is no 0 here. Okay, so all the customers who were given loans, they basically had cars. Okay, then we have gender, male, female. We have their marital status, and this is the dependent variable, which is loss in thousands. Okay, so if a customer defaulted, by what amount did they default? So you can see it only has those customers who defaulted, okay, by at least some amount. Okay, so this is the second level of analysis that they are doing. The first level will be a a classification problem where once a customer applies for a loan, you basically decides whether should I give him a loan or not. But this is not that stage. That stage we will see maybe tomorrow or on the next week we will see that. Okay, we have that as well. Okay, and this is the second case where once you have given a loan to a customer, you basically decide if he is defaulting, what is the probability of him defaulting. Okay, so what is the use of this? The use of this is basically, let's say, so this is from the past data. So whatever data has been given to us, this is past data. So from here, the bank will come up with a model, and that model will tell the bank that, okay, which customer like will default and by how much amount. Okay, now if they have this information, they can apply this model to the future data, and they can take actions accordingly, right? So let's say if they find that there are some customers who will default by a large amount, so they can maybe don't they can, since they have already given them loans, what they can do is they can place regular checks in place. They can send them reminders, or the bank people, I have heard, I'm not sure what they do, never worked in a bank, but the bank people, they also sometimes they send third person, a middleman, they send, and they threaten the customers that if they don't repay their loans, their properties will be sacked and so many other stuff. Okay, so they can do all those things also to get their loans back. Okay, but anyways, that is not a data science problem. That is up to the bank to decide what they want to do. But our problem is to tell in the future which customer will default by what amount. Okay, so the most risky customers for us will be the ones who are defaulting by the maximum amount. Okay, guys. So shall we start with the coding part? Sharmin, don't worry, we can get started. I will anyway show you all. You will have all the data. I have sent a mail, so you will have it. You can follow whatever I'm talking. Okay. Okay. So let me open the Jupyter notebook now. So this is the file. Okay. Okay. So I have briefly described the problem statement as a comment here. So in case somebody doesn't get time to look up the Word document, you can also get the context by looking at the comments here. Okay. So loss given LGD stands for loss given default. Okay. So what is the loss the bank would incur given that a customer defaults? So it means when a customer at a bank defaults on his loan, how much money does the bank lose? Okay. Please don't mind the spellings. Okay. The customers might have paid some amount back or no amount at all. Okay. Some customers, they don't pay even a single EMI and they just default. Or some customers, they are towards the end of their pending amount and they default. The bank wants to know if the amount the bank loses can be predicted. For new customers who apply for a loan, Okay, from the past data of all defaults. So the bank wants to know if the amount the bank loses can be predicted for the new customers who apply for a loan from the past data of all defaulters and their pending amounts. Okay, so this is the context again. Okay, so what are we doing here now? Now we are importing the library. So until now, whatever you saw, we saw the different data types in Python. Then we saw how do we manipulate data, right? We saw group by functions, and we saw how do we select a particular row or a particular column. How do we index in a data frame? We saw all of that, right? So we saw some visualization also. So we learned how to do histograms, how to do bar plots, how to do box plots in Python. So now we'll be using all of those skills. Okay, so that was basically setting the context for doing our modeling stage. So the modeling stage starts today. So we will be importing all the libraries that will be required. So you can do this as and when required. Also, you need not import all the libraries at the first line of your code. Because you might not know, right, which libraries you'll be using. But there are not many libraries in Python. It's not like in R that you have a separate library. There are hardly 5 or 6 libraries which we mostly use. So what we do is we mostly import all the libraries that we feel we'll be using. Okay, for example, pandas. Of course, we'll be using pandas, right? Because data frame is inside pandas only. So pandas is a must. Again, NumPy will be using because some mathematical operations we usually do. So NumPy also we use. So I have imported NumPy as well. I have imported matplotlib because we'll be doing some visualization also, right? So guys, remember all of this, right? We did all of this: matplotlib, NumPy, pandas, Seaborn. You guys remember this, right? Guys, do you hear me? Can I get a response? Remember all of this? Okay. Okay. Now, did I tell you why do we use this matplotlib inline? So this we use so that we get the plots in the same line. Okay. If we don't use this, we won't get the plots. Okay. So this is specific to a Jupyter notebook. If you are using some other IDE, let's say if you're using Spider or PyCharm, then you did not have to write this line. But in Jupyter, you have to write this line. So just a code for getting the plots. Okay. Okay, so I think I told this before. Swati knows about it. Okay, then these models you will see. Why did I write all of this? Because we are going to do a linear regression model, right? So to see the output of a linear regression, we use this. So you can see stats model. Okay, so don't worry about this. I'll explain you this when we get to that. Okay, yeah. So we'll start by reading our files. Okay. So reading a file in Python is similar to how you read in R. In R, we use read.csv. Here we use read_csv. Okay, and read_csv comes from pandas package. This function is present inside pandas package. So you will have to use the initials of the package. We already gave a short code to pandas, right? We wrote import pandas as PD. Now PD will represent pandas. So I have written pd.read_csv. Okay, so let me run this line. Let me import all the libraries first. And then yes, Sharmin, that is a programming practice, a good programming. That is so commonly used that people have started using it. Everybody has started using it. You can use some other code also, but you will be the first one to use it. Basically, wherever I see or whoever imports Python, he always codes it with PD, not with any other character. But you are free to do that. No, it's not fixed. You can change it. You can write PDS also if you want. Okay, so this star means my code is still running. So too many libraries I have imported, so it will take some time. So once that is done, I will import my file, the CSV file which I showed you. I'll import the file, and then we will start some basic exploratory data analysis. So this is a case study. So we will see how exactly a a life cycle of analytics project looks like. Okay, how do we collect the data? So we have collected the data from a CSV. In the industry, you might not always get the data from a CSV. Sometimes you get it from multiple resources. You get it from CSV. Sometimes you will get it from the internet, or sometimes from a SQL database. So or sometimes from all of this, and then you'll have to combine the data sets. Okay. So now it's done. Now I will read the CSV file. So I have given the location, so I don't have to set my home directory. It will read from this particular location. Oh, I got an error. So that means my data set is not in this location. Let me just check. I think I gave the wrong location, which is inside linear regression, whereas here it is logistics. So this is wrong. Okay, and the slashes don't work in Python. In Python, it uses the max slash. So either you give double slashes or you give the backward slash. Okay, now it should work. Okay, now this data frame has been read. So the CSV file that I showed you is read as a data frame DF now. Okay, so DF is a data frame. We will start our exploratory analysis on this data frame now. Okay, let's go ahead. So let's do a basic EDA. EDA stands for exploratory data analysis. Okay, exploratory data analysis, if we haven't talked about it, is where you clean your data, where you identify outliers, where you do some basic statistics on the data, you draw some plots on the data. So whatever you do basically to get an overall understanding of the data before the modeling stage is known as EDA. Okay. So before modeling, whatever cleaning you do, whatever imputations you do is all of that comes under EDA. Okay. So now I'm just trying to find how many rows and how many columns are present in this data. So for that I will run DataFrame.info. Okay. This tells us, so this will give us this as the output. So let me run it quickly. So this is the output I get when I run DataFrame.info. So it is telling me that there are 15,290 entries. Okay, entries is nothing but rows. Okay, records or observations you can say. So there are 15,290 entries. Okay, 0 till this number. The index starts from 0 in Python, and there are seven columns. Okay, which we saw already. There are 7 columns in the data, and it also tells you some details about the columns that we have. So account number, there are these many non-null values. Okay, age also, there are these many non-null values, and so on. So if there are any missing values, you can identify from here. So we don't see any missing values, right? All the columns have 15290, and there are 15290 rows also, right? So none of the columns has any missing values. So on the missing value part, we are good. Okay, tomorrow we will see. So in this data I have not included all the complexities, but in tomorrow's data set we will see that we'll have some missing values, and we will try to impute the missing values, okay, using some logic. But today we are starting in a simple way. We do not have any missing values in this data. Okay, cool guys. Okay. So just like you have the head command in R, I'm sure you would have used the head command in, right? So in R we write head and then the data frame. In Python we will write DataFrame.head. Okay, so that is how the syntax usually is. Okay, so if I have to show you, if I have to write the syntax of R versus Python, so this is how it usually. Okay, so in R usually the syntax is first you write the function, okay, and then you write the variable name. This is how it works, but in Python it is opposite. You first write the variable name, you give a dot, and then you write the function. This is how it usually works in Python. Okay, so just remember this. Not a big deal. So for example, you will write head of data frame in R, but in Python you will write data frame dot head. Okay, and so on. If you want to find the max of something, you will just write max of the variable name. Here you will write x dot max. Okay, I'm not sure if this works, but yeah, this is how the usual process is. Okay. Okay, so I have done a head of the data frame just to get an idea of the data frame. So it shows me the top 5 rows, okay, from the index 0 to index 4. So these are the account numbers, the age, the years, number of vehicles, gender, married, and losses in thousands. So these are the losses in thousands. Okay, so this particular customer, he did not repay a loan. Like this was not the total amount that he took, but this is the amount that he did not repay. Okay, so $203 is what he did not pay. Similarly, this guy did not pay 400. This is a female, so this girl did not pay 402. Okay. Oh, she's 31 years old, so this lady did not pay $402, and so on. Okay, so there are too many things that we can try to find here. So we can try to find that does the loss the bank incurs due to a default, is it dependent on the age? Is age a factor using which we can decide whether a person will default or not? So are younger people defaulting more, or are older people defaulting more? So that is a question that we can ask. Then similarly, based on the years of experience, so people who have less years of experience, are they more likely to default, or are they defaulting by a larger amount or not? So again, these two variables might be correlated. So there might be some correlation between the two, right? So these two independent variables, because obviously as your years of experience increases, your age will also increase. So we will see some correlation between two. So that also can be studied. Linear regression correlation is a problem, right? We all know that. So we will have to check the correlation here. Then the number of vehicles. So can we decide based on the number of vehicles whether a customer will default or not, or will it default by a larger amount or not? Similarly, gender. Do male default more or do female default more? And similarly, married. Do single people or do married people default more? So these are the questions which we can try to ask by this analysis. Okay, and we will try to include all of these variables together in a model. So that's the advantage of using a model. Okay, if you have to just analyze one variable at a time, we don't need a modeling for that. We can do it using just bivariate analysis. So bivariate analysis is where you analyze two variables at a time. Okay, so that can be easily done. We don't need a model for this. But when you have to analyze more than one variable, okay, so for example, age plus number of vehicles plus gender plus married, all of this you have to see with respect to loss in thousands. That is where we need modeling. Okay. Okay, so let us start with some plots. So the first plot that we would be doing is, okay, we have some questions. Yes, Sharmin, you have to type the entire location. Okay, yeah, Amrachi. Don't you guys know the head command? Yeah, head command gives you the top 5 rows. Okay. The head command will give you only the top 5 rows. The dataset does not have only 5 rows. The dataset has 15,290 rows. We saw that here, right? So these many rows the dataset has. But when you do a head command, it shows you only the top 5 rows. So index 0 till index 4. Okay. No, Amrachi, no reasons why do you take just 5 records? Because see, head command is done just to get an overall look at the data. Okay. Now the overall look you can get using five rows is enough to give you an overall idea of the data. Yes, exactly. You can look 10 columns, 10 rows also, but 10 rows will again clutter your screen. So 10 doesn't make sense. If you use just 2 rows is maybe very less to get an idea. So we generally use 10 rows, but you are free to use more also. So you can write just 10 here. If you want 10 to see 10 rows, then you will get 10 rows. So see 10 rows, it is cluttering the screen. It is filling your entire screen. So it is not looking good. Or if you use just 2 rows, it might be too less. too few. So just 2 rows will not give you a good idea. So we generally don't write anything, and by default the number is 5. So it gives you 5 rows. It doesn't clutter your screen. At the same time, you get plenty of records to see. So you get a good understanding. So that is why the head is used. Okay. Jagdish, I think I answered your question as well, right? Okay. So head, you know, right? The literal meaning of head is like the top of your body, right? So it shows the top of your data frame. Okay. Similarly, there is a tail command also. So if I write tail, it will show me the last 5 rows. Okay. So you see the index now. It is 15285 till 15289. So the last 5 rows are being shown. So you can do this also, because we were not concerned with the top 5 or the last 5, right? We just wanted any 5. So any 5, either head or tail will do, to get an idea of the data. Okay. Now we will start with some visualizations. Okay. To get a good understanding of the data, we will have to do some visualizations. So these visualizations, you can say we are doing a univariate analysis. So let me just write what does it mean. So get rid of this. Okay. So first we will do a univariate analysis. Okay. So what is univariate analysis? Where we analyze only one variable. Okay, this is univariate analysis. So how do we analyze one variable? So can somebody tell me, how will you study a single variable? Guys, how will you study a single variable if you have to study one variable? Yes, Praveen, you are right. We will use histograms. Okay. Any other ways you can study a single variable? Sharmin, how will you draw a linear plot for a single variable? Yes, Rajesh, you are also right. Boxplot, we can use boxplots. Linear plot requires two variables, right? A x-axis and a y-axis. So when you have just one variable, you can have either of the axis, not both. So you cannot use a linear plot. Okay, Sharmin? So yeah, we can use histograms, we can use box plots. What are the other ways we can analyze a single variable? It need not be a plot, okay? You can say anything. Pie chart, Sharmin, pie chart you can draw if it is a categorical variable. But yeah, this is correct answer. But pie chart can be drawn only if it is a categorical variable. So for example, let's say it's gender, and you want to know that what proportion of gender is male and what proportion is female. So you can draw a pie chart for that. The pie chart will tell you that, let's say 60% is male and 40% is female. But if it is continuous, you cannot draw a pie chart. Yes, Rajesh, you are right. We will use descriptive statistics for that. So mean, median, mode, standard deviation. Aisha, scatter plot again requires two axes, x and y. So you cannot have a scatter plot for a single variable. Okay. Okay. So this is how you do. So one single variable, when we analyze one variable at a time, this is how, these are the few items which we can use. Okay. And we usually start with this. So we can do a descriptive statistics on the variable. Okay. So descriptive statistics is just a fancy name for mean, median, mode, standard deviation, okay, variance, etc. Not etc. I think these are all. There is nothing remaining. Okay. So these are the things which we do, which we can do for a single variable, for a univariate analysis. Okay. Then, as you said, we can draw some histograms. We can draw box plots. Okay, pie chart we can draw, not used commonly, but we can draw only if it is categorical. Okay. Yeah, I think that is all. There is nothing else that you can do. Box plot. Yes. So this is what you can do if you have a if you have to do a univariate analysis. Okay, one variable at a time. So let us see. So we are trying to. So what we are trying to do here is we are trying to draw the histogram for the dependent variable. So losses in thousands is our dependent variable. We are trying to draw a histogram for that. So you remember this distribution plot we discussed this in the last class. Okay. So don't worry, all these things you were not supposed to remember, but if you Google, you will get histogram. You should remember because it is very commonly used. So you should remember this function, dist plot. Okay, distribution plot. It stands for distribution plot. Histogram is one of the distribution plots. Okay, because histogram is nothing but it shows the distribution of the variable, right? So it is also known as distribution plot. So this function, distribution plot. So this function comes from the Seaborn package as we discussed last week. So SNS dot dist plot, and I write the variable, okay, which variable I want to plot, and KDE is nothing but that line that you get, right? I have given it false, so that line is not coming. Okay, if I write it as true, you will get a curve coming. Okay, so if I run this, oops, okay, so you see that line, right? That curve coming, that is known as the KDE. That is not required, so I can make it false. Okay, so this is the distribution, and bins, I think we discussed what are bins in the last class. So bins represents how many bars do you get. Okay, so let's say if I give it a smaller number 10, you will see only 10 bars present. Very few bars will be present. Okay, so this does not give you a good idea about the data, right? Because the bars are too wide. So I should make it slightly bigger, so maybe around 50 or 60, 70 is good. So I can try with 70, then I will see some detailed information. So now the bars will be smaller and I can see a more detailed picture of the distribution of data. Okay. So this is how our data looks like. So see, looks like there are some customers who have almost zero losses. Okay, the bank has incurred losses of almost zero due to some customers. So not exactly zero, because this is on the right side of zero. Okay, so even values like 10 to 20 or less than 30 are looking like they are zero. Okay, but we don't have any person who has not resulted in a loss. So the dependent variable is not zero. The minimum value that we saw was 13, I think. Okay, so all of those are coming here. And if you see on the higher side, you have some customers who have defaulted by almost, like, it goes continuously till 2000, and you have some gap here, and then you have these some guys here, right? So you see some 3000 also, some 3500 also. So there are some customers who have resulted in a loss of almost $3500. Okay, so it's a right skewed figure, right? This is what is known as a right skewed histogram. So you all know, right, what is a right skewed histogram? Tailed is another name for right skewed. No, Paridhi, if you have imported a library once, it is done. You don't have to import it every time. I was not sure if I have imported earlier, so I wrote it again. Okay. Importing it once is enough. It's just like ours. Only once you do. Okay. Amrachi Jagdish, you got right. What is KDE? I saw your question now. Okay. Okay. So similarly, I will do so the other continuous histograms are drawn for continuous variables, right? So the other continuous variables that I have is age. Okay. So I'll try to draw the same histogram, the same function for age now. And this is how it looks like. Okay. So if I draw for age, it looks like this. Okay. So this is how the age is distributed of all the customers. Okay. Yes, Pari, the histogram is used for univariate analysis. Okay. Because it has only one axis, right? We are just analyzing one variable at a time. So the x-axis is the variable and the y-axis is the frequency. Okay. Amrachi, the y-axis is the frequency. Okay. The y-axis of a histogram is frequency. So let's say, for example, let's say I have age. Okay. I have values 5, 11, 21, 30, and 35, and again 12, 16, 19. Okay, these are the values of age I have. Let me draw a histogram for it. So I just have one variable, right? So my x-axis will be age, and my y-axis will be the frequency. Frequency is nothing but the count. Okay. Now let's say I have these bins. So this bin is, let's say, 10. This is 15. This is 20, 25, 30, 35, 40. Okay. Now I will see how many records come close to 10 years. Like, yeah, close to 10 years. So we have this, which is below 10. This is close to 10. This and this. So how many we have? Okay, 10. So we won't count this. Okay. This will come close to 15. So I won't count that. Only 5 and 11. So 2 records, right? 2 records are between. So I will take this to 2. So the height of this bar will be 2. Okay. Now I will see which are closer to 15. This is 15. This is 15. And any other 15? No, this is towards 20. So this will again be 2. Now 20. This is 20. This is 20. So this is again 2. 25, we do not have anything 25, so it will be 0. 30, we have only 1, so it will go till here. 35, we have 1, so again this will be just 1. So this is the same bar. Now we had only 6 or 7 values, right? So it looks like you have these bars. But if you have too many values, imagine you have hundreds, thousands of values like this. So for in our example, we have 15,000 something, right? Something values. So the bars will become very small. Okay, it will become very small and they will look something like this. And that KD is nothing but it will just plot something on top of it. So it will show you the distribution. How is it distributed? So this is histogram. Okay. Clear, guys? What is a histogram? What is on the y-axis? Okay. Okay, and the same thing I have done for years of experience. So you see both of these look very similar, like the age of the customers and the years of experience of the customers, they look very similar. They have a peak at the beginning and they have a peak at the end, and they are almost they look almost uniform in the middle. So same is for the experience, because of course we know that these two are related, right? If your experience increases, your age also increases, or rather if your age increases, your years of experience also increases, right? So they look very similar. Okay. Now let us come to the categorical variables we have. So we had 2 continuous variables among the independent variables. One was age, one was years of experience. Now let us come to the categorical variables. So the categorical variable that we had is, for example, the first one, gender. Okay, we had gender, we had the marital status. Okay, so let us try to analyze this. Now we cannot draw a histogram for a categorical variable. Histograms are drawn for continuous variables only. It will not make sense, right? How can you draw for male? There is only one value which is male, so you cannot draw a histogram for that. So in those cases we can draw a box plot. Okay, so I'm trying to draw a box plot here just to detect the outliers. Okay, so I'm trying to draw a box plot with respect to the dependent variable. So losses in thousands. I'm basically trying to see if my losses in thousand is dependent on the marital status. Okay. So see, this is how I do. I draw this. I import boxplot function from the Seaborn package, and on the x-axis I give the marital status. Okay. So x-axis is married and single both, and on the y-axis I give the dependent variable, which is nothing but loss in thousand. Okay, and they both come from this data frame. So I have given data is equal to df. Okay, now hue is equal to gender. This is used if you want to give different colors. Okay, so this is not a univariate analysis. You can say this is a bivariate analysis, but we have three variables into consideration. The first variable is the marital status, then it is the losses in thousands, and the third dimension we are adding is gender. So we are adding a color also. So that is adding the third dimension to it. So according to the gender, we are analyzing if married people versus non-married people have any influence on the loss in thousands. Okay, and with respect to gender also. So let us see what we get. So this is the drawing that we get. So we are getting married and we are getting single. Okay, now what do you infer? What can we infer from this drawing? So who can tell me? So let's talk about males first. So do you think bachelor males are resulting in more losses, or married males are resulting in more losses? What do you think from this diagram? Swati, this is not exactly bivariate analysis because you have three variables. Bivariate is when you have two variables. Okay, this is not a bivariate as well. Okay, so male bachelor is resulting in more losses, or male married people are resulting in more losses? What do you think? Okay, bachelor singles. Okay, so people say that single people are resulting in more losses. Okay, why do you say that? Yes, male bachelors are resulting in more losses, but why do you say that? Width of the box. No, Sharmin, the width of the box is not important here. Okay, Jagdish says outliers are more. Not exactly. Not exactly, guys. Outliers, you don't decide based on outliers, okay? Outliers are exceptional values. You don't make a decision based on exceptional values, okay? So what is it then? Did I explain you box plots? Have I explained box plots in the past classes? Okay, let me cover it. Rajesh, you are right. It tells you about the quartiles. Okay, let me cover it. Okay. So this is what box plots are. Okay, let's quickly discuss about box plots. So a typical box plot looks like this. Okay, their primary usage is to detect outliers. So whatever outliers will be present, and this is again used for univariate analysis. Okay, because we have just one variable, right? We analyze one variable, but it can be used for bivariate also. So in our particular case, we are using it as for a bivariate analysis because we have added other two dimensions, or it can be used for more also. Okay, if you are adding more dimensions to it, you can use it for more. Okay, so what do we do? So whatever outliers you have, they will come as dots here. So you would see some dots, right? In some of the figures, you see some dots. So these dots are nothing but these are outliers. This is also known as box and whisker plot. Okay, this is the full name of it. In short, they are known as box plots. Okay, now what does this represent? Okay, this box is very important. Okay, this box represents 50% of your data. 50% of your data will be in this box. Okay, and the remaining 50% will be outside the box. Okay, and you would see a broad line in the middle. Okay, in the diagram you will see a broad line. That is nothing but the median. Okay, and median is nothing but 50th percentile. Okay, this particular line, this line is the 75th percentile. This line is the 25th percentile. This is known as first quantile. This is known as second quantile. This is also known as third quantile. Okay, so this is what it represents. Now this distance that you see here, this distance and this distance, and you see some distance here as well, right? This distance is known as interquartile or interquantile range, IQR. Quantile or quartile also, okay, they mean the same. Okay, this is nothing but 50th percentile, oh sorry, 75th percentile minus 25th percentile. Oops. Okay, now what about this distance? What is this distance? This distance is third quantile plus 1.5 times IQR. Okay, similarly this distance is, can somebody tell me what is this distance? This is first quantile minus 1.5 times IQR. Okay, so this is what box plot represents. So too much information in one simple plot. Okay, now how does it help us to identify outliers? Usually we consider points which are greater than, which have a value greater than third quantile plus 1.5 times IQR, or values which are less than 1 quantile minus 1.5 times IQR as outliers. Okay, so this much information we get from a box plot. Clear, guys? I hope box plot is clear to everybody. Yes, please respond. Is it clear? Okay, great. So didn't I cover the box plots, or wasn't it covered in our classes? Okay. May I know who took your R classes? What was his name? His or her name? Okay, no problem. Okay, so now it is pretty clear, right? What each line in a box plot represents and how do we identify outliers in a box plot? Okay, so now give me the answer to the same question. Why did you say that male bachelors result in more losses from this figure? Why did you say that male bachelors result in more losses than married bachelors? Yes, tell me. I'm waiting for answers. Yes, correct. Exactly. So Aisha gave the right answer. The median line is what you will consider. Okay. So if I bring back the diagram, this median line is important. Okay. This median line, this is very important. You cannot rely on the outliers because they are the exceptional values. Only a few records are here. You cannot rely on these, but you can always rely on this, right? Because this is 50% of your data. This might be, let's say, only 1% of your data because 50% is here and the remaining 50% is from here to here. So that means if you consider only these points and these points, they will hardly be 1 to 5%. So you cannot rely on the outliers to make a decision like that. But median means this is the average, kind of average of the 50%. Okay. So this tells you that where exactly is most of your data points located. So based on the median line, you will decide. You made that decision. Okay. It was pretty clear in the graph, but you were not getting the words to say that basically. So this median line, if you see for single people, for single male, so male are denoted by blue color. So the median line for the blue single box is far greater or greater in y-axis than the median line for married male, right? We see that difference here. That is why we conclude that single male result in more losses to the bank than married males. Okay, and it sounds logical also, right? So single male, probably less experience, maybe less income, so he might default. So his life is more fickle, right? So he has more he defaults by a larger amount. Okay, so let us move ahead. Now let us find correlation. We earlier found that two variables were very similar to each other, right? So we found distribution plot of age, and we found distribution plot of years of experience, and we know, like by common sense also, we know that these two variables are correlated. And one of the primary assumptions of linear regression is that there should not be any correlation between the independent variables, right? All of you know this, that there should not be any correlation between the independent variables. So let us first see if there is any correlation, and if we find any correlation, we will have to basically treat it, or we'll have to do something about it. Okay, so let's first measure that correlation. What is that value? So correlation in a data frame in Python can be found using DataFrame.CORR function. Again, this is following Python syntax. First we write the name of the variable and then the function. In R, you do it using COR function. You just write COR and DataFrame. Here we write DataFrame first .CORR. Okay, the function is slightly different. It is CORR. Okay, so now we get these values. Okay, and this function is smart enough to find the correlation of only the numerical variables. It will not, if you do the same in R, you might get an error because you have gender and marital status, which are categorical variables, so it will throw error. So you will have to individually select the numerical columns and then pass it. But here Python is smart enough to detect, and it will find you and it will give you the values. So we see a high correlation between age and years of experience. So this is your age and this is years of experience. So you see there is almost 100% correlation. So 0.997, which is almost 100% correlation, which is obvious as with age your experience increases. Okay, yeah, this is obvious. Okay, so we will keep a note of this, and during our modeling stage, we will see how this affects our modeling. Okay. Okay, Amrachi has a question. If you say y-axis is the frequency, how come the age histogram has very big numbers on the y-axis? Okay, let's go back to the histogram. You're talking about this figure, Amrachi? Okay, which other? Age histogram, age. This one? This one? Okay. So why does it have a large value? Because you have so many people who are, let's say for example, this one. You have these many people, so almost how many? 800 plus people who have age around 70. That is why you have this big bar here. Okay, got it? Similarly, if this value is around 15, the starting value, if it is, let's say, close to 15, you have around 900 people whose age is close to 15 years old. That is why you see that big bar here. A Paridhi age, see, univariate analysis is when you analyze one variable at a time. Okay, so this is a univariate analysis because I have taken only age, nothing else. I'm not analyzing two variables together. That is why it is known as univariate analysis. Okay, univariate. Uni means one, right? Uh, Sorry, Amrachi, do you want to know the function, the formula, how this correlation is arrived at? How does this value come? Do you want to know that formula? Okay, so I'll talk about the formula. That might not be required, but anyways, I can talk about that formula. Okay, so just for a quick, how do we find correlation? Okay, anyways, we should know this actually. As data scientists, we should have this information, though we don't use it because we use a software package to find the correlation, but we should have a good understanding of how that correlation is found. Okay, how is the correlation calculated? So let's say correlation is always found between two variables, right? Between two continuous variables. Okay, you always find the correlation between two continuous variables. Let's say we have a variable x, we have a variable y. Okay, we have some values of that variable. Okay, we have to find the correlation between x and y. Both are continuous variables. Okay, now we can always find the mean of x. How will we find the mean of x? We will just sum all the values of x divided by n, right? This will give us the mean value of x. Similarly, we can find the mean of y. We will sum all y divided by number of y's. Okay, and both should be equal numbers. Okay, then only you can find correlation. If this is, let's say, 5 and this is 10, you cannot find the correlation. It will throw error. You should have equal number of points. Okay, so 1, 2, 3, 4, 5. So both should have 5 number of points. Now similarly, you can find the standard deviation of x. Let me represent it like this. Standard deviation of x, and similarly I can find standard deviation of y. Correct? How do we find the standard deviation of x? Do you recall the formula from your R classes? Yes, who can tell me? How do we find the standard deviation of a variable? Just reply yes or no if you remember or not. I don't want you to type the formula, but do you remember the formula? Okay, so people do remember. So the formula looks something like this. So you will have individual values of x minus the mean of x whole square, summation of this divided by n, right? So standard deviation is nothing but root mean square of deviations from average, right? So I've taken the average here, taken their deviation. So we get the formula if we start from the back side. So first take the average. Average is nothing but x bar. Okay. Then deviation from average. So xi minus x bar is the deviation from average. Then root mean square. So first square it. I have squared it. Then you take the mean. I have taken the mean by dividing by n. And then you take the square root. So I'll take the square root now. This is the formula for standard deviation. Similarly here it will be yi minus y bar whole square divided by n. Okay. So this way you get the standard deviation and the mean of both x and y. Okay. Now what we do, we calculate standardized x. Okay. Similarly we calculate standardized y. Now what is standardized x? This is nothing but xi minus x bar by sigma x. Similarly this will be yi minus y bar divided by sigma y. So these are the formulas for this. Okay. X bar you already know from here. Sigma x you already know from here. You can put these two values for each value of xi. So what if xi is 1, you will do 1 minus this number by this number. Similarly if xi is 2, you will do 2 minus this number by this number, and you will get these values. Okay, clear till now everybody? You get these 5 values. Okay. Now what do you do? This is not standard deviation. Okay, this is standardized. This is standardized x. Don't mind the spellings. Okay, this is standardized x. Now what do? You just multiply them. You multiply standardized x into standardized y. So this into this, you get some number. This into this, you get some number. So you get 5 numbers. Okay. At last, you take the mean of this. Mean of this entire column. Okay. That is nothing but your R, or the correlation. This is how you find correlation. This is what the function does. And this is what you can do if you're doing it manually. Clear, guys? Is it clear? Okay. So there are so much maths involved in analytics, but since we use the software, we often don't understand the underlying maths behind any problem. Okay. Okay, cool. So let us move ahead now. Okay. So this is how we find correlation, and we observed that there was a high correlation between age and years of experience. Okay. So 0.99, which will be an issue in linear regression. So we'll have to do something about it. And if you see the other correlation values, we don't see much correlation between the other values. So for example, the other big values that we see is this much, this one. Okay. But this is a good correlation, right? Because this is the correlation between the dependent variable and our independent variable. So this is something good for us. The more the higher the values here, the better for us it is, because age will help us in explaining the losses in 1000. Okay. But between independent variables, there should not be much correlation. So if you see the other independent variables, you don't see much correlation. Okay. So other places we are good. So this is the only thing which can create a problem, and we will do something about it. Okay. So next we will start with some small models. Okay. Before we jump to the final linear regression model. So guys, can we quickly take a break now? Okay, so that you guys basically refresh yourself, because we will start with the modeling part. So I want you to be attentive then. Okay, so let us take a 15 minutes break. Shall we take a 15 minutes break, and we will take another break towards the end also. Okay, maybe around 1:30 or 2 o'clock we'll take another 15 minutes break. So we'll take two 15 minutes breaks. Okay, so let us take a break for 15 minutes. Let us be back by 12:45. Okay, so 12:45 we'll start again. Okay, so I'm going on mute. Okay, I see you then. Hi guys, are you back? Guys, are you there? Okay. Which places are you from, guys? I am from Bangalore. Anybody from Bangalore? Okay, Paridhi is from Rajasthan. Jaipur, okay. Mumbai. Okay, Shovarani is from Bangalore. So there are some openings at TCS right now. So if you guys are interested, you can apply. Oh, Lonavala. Oh, I think they have openings in TCS Bangalore as well as in Pune. So some of my students, they just gave interviews, and a few had given interviews last month and they got selected. So they have joined in Pune. So one student has joined in Pune. Yes, they have for all levels of experience. I think from 2 to 8 years. That is what they are looking for. Like the total experience should be 2 to 8 years, but they are considering if you have even 1 year in analytics. And with this course, I think you should be able to show 1 year in analytics. So this project, for example, the current project that we are doing, you can show this as a project in your office. Aisha, I'm not sure if the TCS opening is for fresher, but keep searching. There are openings. I'm not sure if TCS is considering freshers, but some other companies will. And as a fresher, it is easy actually. So as a fresher, it is easier. Paridhi, there is no concept of developer in data science. Okay, so that is only for software. So you should know the domain as well as a little bit of coding. So it's not like developer in data science and tester in data science. That concept does not apply here. The concept of data engineer is there. Okay, so you can either be a data engineer or you can be a data scientist. Okay, data engineer are the guys who basically they do more of SQL and collecting the data. So they don't do this modeling part. But data scientists, you are mostly selected for the modeling part. Okay, the EDA and the modeling. Okay, data engineers, they will just collect the data in whatever format data scientist needs, and they will give it to the data scientist. That's it. So everybody is back. Can we start? Okay. Amrachi, where are you from? I think I took an introduction, but I missed. You are from Nigeria, yeah. So how is the job market in Nigeria for analytics? Okay. So there is, yeah, because yeah, so there is a lot of requirement. Okay, good, good. So this course, I'm sure it should help you. It should help you basically move into a full-time role as a data scientist. Yes, that is true. That is true in India as well. So even in India, the big MNCs, the multinational companies, or the big Indian giants like the Tata and Infosys, they have basically grown a team of of data science. But if you see most of the other Indian companies, they are yet to scale up. So they are still figuring out which way they should scale up. Should they hire trainers from outside, or should they hire people who know data science and train their employees? So they are still figuring out. Yeah, Amrachi, it is lucrative. Yeah, so analytics and other guys also. So analytics industry, the sooner you jump into it, the better it is, because the competition gradually increases, right? And not gradually, at least in India, it is increasing sharply, the competition. So the sooner you learn and the sooner you jump, it's the better it is, because after 2 years, I'm sure it will become difficult. It will become saturated, just like the IT industry. Okay. Aisha, yes, you can mention these projects in your resume. So for people who have worked in finance domain, you can basically camouflage this project as an actual project of your company. Okay, you'll have to make some changes. See, that's what my past students have done. Okay, they have taken these projects and they have just written some written it beautifully, so that it sounds like it's a big project of a bank or something. And questions will be asked, so you should be ready for the questions, because a lot of questions will be asked if you show this as a project. But if you're able to answer the questions, the interviewer should be good with that. Okay. Amrachi, you can search on LinkedIn. So there are many opportunities on LinkedIn. Just go to LinkedIn and search, go to the job section there, and look for data science jobs. You will see the profiles. What do they look for? Okay. But yeah, don't get scared, because the job descriptions, the JDs are usually prepared by HR people. Okay, and HR people, they don't know the technical skills, so they will mention tens of hundreds of technical skills there. Okay, but yeah, even if you match some 50 or 60% of it, you can apply for that profile. No, no, I was not referring to any. Yeah, I did refer to a specific one, which is at TCS here. So TCS is the acronym for Tata Consultancy Services. I'm not sure if it's there in Nigeria, but it is present in a lot of countries. So they have some current openings for their Indian locations. So that is what I was referring to. I don't have the JD for it right now. I just heard it from my students, because my other students, they have been interviewed there uh, a few days ago. So just heard it from them. Just look for the opening. So just Google maybe at Naukri, or you can find it on LinkedIn and apply for it. So all the processes would be mentioned there. Yeah. So Praveen has seen the JD. So okay. So it is for 0 to 18 years of experience. So I think everybody can apply. So freshers can also apply. Yeah, but you can try now, but yeah, if you can revise whatever you have learned and take some time for yourself and then apply, it would be good. Because if you apply now and if you're not confident, you might get rejected, and that would be a big discouragement. And you may not be able to apply again for the next I don't know what term they have, maybe 6 months. You will not be able to apply again. So better wait for maybe 1 or 2 months and revise everything and then apply. But again, that can also turn out to be bad, because the position might get filled. So you take a call. Okay, Amrachi. Okay, great. So I hope the course will help you. Okay, guys. So let's move ahead now. Okay. Okay. So now we will come to. Okay. So let's see what I have done here. So I have written, first, let us build a simple model with all variables as is. Okay. So okay. So one thing to be discussed here is, Do you guys know about the concept of dummy variables? Has this been covered in your R classes? What are dummy variables? Okay, okay, this is strange because without dummy variables, it will be difficult for you to understand linear regression or logistic regression. No, Aisha, it's not training and testing data set. Dummy variable is a different concept. Okay, let me explain it. So let me take a new sheet. Okay, but linear regression was covered to you, right? Linear regression, logistic regression, this was covered. So then you should have had this question in your mind if linear regression was covered. Let's say I was doing linear regression, okay? Or imagine I'm doing logistic regression, whatever. And let's say you have variables like income. This is your dependent variable. And you have, let's say, age. This is the independent variable. You have gender, okay? Male and female. This is also an independent variable. This is a continuous independent variable. This is a categorical independent variable, okay? And we will try to do a linear regression on this. Just two variables, we will do a simple linear regression. So we will get a output like this. So in a linear regression, we get something like this, right? Beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 beta n xn, right? This is what we get in linear regression. So in this case, our y is income. So we will get something like income is equal to beta naught is nothing but the intercept, right? So intercept is nothing but where your line intersects the y-axis. If this is your y-axis, let's say it intersects at the point 0, a, then a is your intercept. So this beta naught will be equal to a. So here it might look like, let's take a guess. So income is equal to 5 plus, now beta 1 is age. So age into whatever is the beta value of the coefficient of age. Let's say it is 10. Okay. So with one increase in your age, your income increases 10 times. Just consider it. I know it's not true. I hope it was true for me as well, but it's not true. And let's say we have another independent variable, which is gender. So let's say now gender. Now here we are stuck, right? How do we, let's say we have a constant k and we have gender here, right? So how do we multiply gender with a constant? So age we can multiply, right? Because age will take numbers like 1, 2 or whatever till 100. Okay, so we will be able to multiply and get the income value. But how do we multiply gender? Gender is not a number, right? It has values male and it has values female. So how do we multiply that male and female with this constant, with the constant beta naught or k? So now we are stuck. So what do you think? What can we do now? So didn't you have this question when you were doing linear regression earlier? Or the same applies for logistic also? Didn't you have this question? Didn't you ask? Guys, I'm waiting for an answer. So tell me, what do you think? Didn't you have this question before? Okay. Okay, so Sharmin is partially correct. We assign values to it. Okay. Okay, so let me show you what we do in these cases. Okay. So now we are stuck, right? Now we have a category and we cannot multiply a category with a constant, right? 5 times male will not make any sense. So we will have to convert these to numbers to get it to this equation. To get it in this equation, we'll have to convert male and female to numbers. So this concept is known as dummy variables. We convert them to dummy variables. Okay, we convert all the categories of any categorical variable. So here we have two categories, male and female, to dummy variables. So how do we do that? Let us see. So let's say, for example, we have gender in this case, right? We have two categories, male and female. Okay, so always remember one thing. So we have two categories, right? So we will have to create new variables for each of these categories. So we will have a new variable, let's say we call it male, and we have another variable, we call it female. Okay, so these are two columns now. So previously we just had one column called gender, which had male and female. Now I have created two columns like that. One is male and one is female. So let's say, and these are the rows. These are the existing rows. So let's say if a person is male, I will give him 1, and this will be 0 automatically, right? A person can't be both, so it will be 1 and 0. Similarly, if somebody is female, we'll have 1 here, and this will be 0. Okay, and so on. Now, do you think both these columns are required to understand, to get this information on gender? Is both the column required? What do you think? Okay, all of you say no. So great, you got the point I was trying to make. Okay, so both the columns is not required, right? So that means if I see that male is 1, I automatically know that this will be 0. Or if I see the male is 0, I automatically know that the person is female. So I don't need one of the columns. Both are not required. I can do without one of these columns. So similarly, if I expand this concept to multiple levels, so here we had just 2 levels, but if we expand it to multiple levels, you will get the same interpretation. So the number of variables, these are dummy variables. These are known as dummy variables, okay? Because they don't really exist in the data, you create them for your own benefit. So we call them dummy variables, okay? They are dummy. We did not get these variables in our actual data. We have created it for a temporary purpose so that we get the equation. So it's dummy variables. So the number of dummy variables is always number of categories that you have in your categorical variable minus 1. Okay, always remember this. So we have two categories here, so we will have just one dummy variable, which is male, or any one of them we can have. Doesn't matter which one you'll have, any one of them you can have. Okay, so this is the concept of dummy variables. Now you have your male and female in ones and zeros. So you know if it is a male, it is 1, so you will write a 1 here, and now k into 1 will become k. So that means your income will increase by k times if the person is male. Okay, and similarly female will have some other coefficient. Your income will increase by that much times if f is equal to 1, and so on. Okay, so this is the concept of dummy variables. Is it clear now? Yes, it's like a virtual column, Amrachi. Okay. Okay, great. So why you did not know this? This should have been covered during R, but in R it is not mandatory because R does this automatically. Okay, you don't have to do it. R does this automatically, and you basically fail to see that R is doing this because the function automatically takes care of this. Okay, but in Python this is required because Python does not do it automatically. You will have to do it manually. You'll have to write some lines of code, and then you have to do it. Okay, okay, Sharmin. So let's see how do we create dummy variables in Python now. Again, reiterating, in R this is done automatically, you don't have to do it, but in Python we have to do it. Okay, so that is what I'm trying to do. Okay, I'm trying to let's build a simple model with all the variables as is. Okay, so for all the categorical variables that I have, I'll have to create dummy variables. Okay, so first I'm creating for gender. So how do you create dummy variables for gender? Using this function. Okay, get dummies. The function name is get dummies. It comes from the pandas package. So I have written pd.getDummies. Okay, so pd.getDummies, then I write which variable do I want to create dummies for. And why I'm writing drop is equal to first is because if I don't do this, Python will create all the categories within that variable. But as we saw earlier, we don't need all. We need one less, right? One less than the number of categories. So I'm dropping the first one. Any one you can drop. I'm dropping the first one. So drop first is equal to true. I'm writing. Okay. So if you see now, if I print that variable, if I print it, I'll get the entire column. I don't want to print the entire column. I'll just print the first 5 columns just to have a look. Okay. So see how it looks. See, this is what we got. We have male 1.00. That means this person is a female. This is a male. This is a female, and so on. Okay. If I had not used this drop is equal to 0, let me show you that as well. Then I would have got both of it. See, now I'm getting both male and female. But I know that both are not required. One column itself is enough to give me all the information. So I will use drop is equal to first. Drop first is equal to true. And then I get this. Okay, cool guys. Everybody, you understood this? Okay, great. Now if you ask me, okay. So Amrachi, we discussed, right, dummy variables. Why we need dummy variables? Because if you don't have dummy variables, you will not be able to multiply a string with a number. Because in this equation, you have a number and you have a value. So you cannot multiply male with k or any constant. So for that, we have to convert the categories to numbers. Now, how do we convert categories to numbers? We use dummy variables for that. The concept of dummy variables. Okay. So dummy variables is just how many categories you have in your data. You basically first create that many variables. Okay. So for example, we had 2 here. So male and female I created, and I just gave them ones and zeros. Okay. I just gave them ones and zeros. Now you see that both the columns are not required. One alone is enough to give you the information. Okay. So you delete one of the columns. Any one of the columns you delete. In the codes, I have deleted the first one. So I have kept only female. Okay. I have deleted female first because you will get in alphabetical order. So female will come first and male will come next. And then I have deleted the first one. Drop first is equal to true I have done so that the first one gets deleted and I only consider the male. So you have your one column which gives you all the information about gender. Clear now? Yeah, the script line also, it's pretty simple, right? So you are just writing get dummies. Get dummies will give you the dummy variables, but you know that one of the columns is not required. You just need one less than the number of categories. So you give drop first is equal to true. It will drop the first column out of it. So you'll get one for female, one for male. You are dropping the female out of it. So you finally have just the male. Okay. In the same way, Swati, if you have more than 2 variables also, it will work in the same way. So let me show you quickly if you have more than 2 variables. So let's say you have color. You have a column called color. You have red, blue, green, yellow. So what are the dummies you will get? You will have red, blue, green, yellow. So let's say a color of some row is red. So you will give 1 and rest will be 0. You will give this 0. Something is blue, you will give like this. If something is green, you will give it this way. If something is yellow, it will look like this. Now again, we come back to the same question. Do you think all these 4 columns are required? No, right? You can delete one of it. Because if we know that, let's say if we delete this. Now we know that if all 3 are 0, that means it is yellow. So we don't need this column. So we can get rid of this column. So how many columns are we left with? 1, 2, 3 columns. We had how many categories? 1, 2, 3, 4. We had 4 categories, but we need only 3 dummy variables. So number of dummy variables is always 1 less than the number of categories. So 4 minus 1, 3. So we need 3 dummy variables. Okay. Now when you write pd.getDummies and you pass, let's say, color, you pass color here, you will get all these 4. But we don't want all the 4, so we will drop the first one. You can drop any others also, but we drop the first one. Just a choice, okay? And we are left with these 3. Now these 3 will go in your modeling. Now these are numbers, so you will have k into some color red. So now you can easily multiply because red is nothing but ones and zeros. So you can multiply with some value. So that issue is resolved, that we cannot multiply red with constant. Now red is no longer red, it is some value, numbers. Okay, clear now? Okay, so let us move ahead now. Now similarly I will do for gender also. Okay, gender I have already done. So similarly for married, I will do similarly for married now, because married also, if you remember, we had categorical, right? Single and married. So I'll do for married also. Okay. So it will look something like this. So I have done for gender. After doing for gender, I have something like this: 1 0 1 0 dot dot dot. Okay. Similarly, after doing for married and deleting one of the columns, I have got, let's say, married. I've got married 1 0 1 and so on. Okay. But I have got these into 2 different data frames. Okay. Because I ran 2 different lines of command for this, right? So I have got it in 2 different data frames. This is df1, this is df2. But I need them together because I have to run a modeling stage, right? So I need all the independent variables in the same data frame, not in different data frames. So what I'll do, I'll just concatenate them. I'll just merge them together. So in R, you will use the R bind function, if you remember. Okay. But here we are using Python, so we will use concat function. There's a function called concat which comes from the pandas package, okay, where you just give the data frames that you want to merge. Okay, so here I want to merge data frame 1, data frame 2, but I don't want just to merge these 2, right? I want to merge the original data frame also that we had, which had the other variables, age, then losses in 1000, the dependent variable, and all the other variables. I want to merge it with that data frame. So all the 3 data frames should come together. So df1, df, df2. So all the 3 data frames, I'll merge them together. So that is what I'm doing here, see. So this is one data frame which has just the dummies of gender. This is the other data frame which has just the dummies of married. Okay. Now I'm merging all the 3 together. The original data frame df, the data frame which had the dummy for gender, the data frame which had the dummy for married. Okay. And this is how it will look like after merging. So I have used the concat function to this. And I think I had already shown you the concat function, right? How it works. Since I'm doing a column merging, I have used access is equal to 1 because I have used cbind of R. If I had to use R bind, I would use access is equal to 0. This was covered in the last class. Okay. So after merging, your data will look something like this. Now you will have all the columns including the dummies. Okay. So account number you already had in the original, age also you had, years of experience you had, number of vehicles you had. Now gender, this is the original gender column which had male and female. I did not touch this. Okay, this is as it was before. Now corresponding to this gender, I created a dummy variable which is this male. Now male is 1 and 0 corresponding to this gender column. Similarly, corresponding to married, I have a dummy variable which is single, which is nothing but zeros and ones. So I have converted these 2 categories to numbers now so that I can multiply it with my equation. Okay. And I have this dependent variable also. So is it clear, this entire thing, whatever we did till now? Video is stuck. Why? I was not moving. Yes, Swati, that is what eventually we are doing. But since it might be multiple categories, here we had just two categories, right? Male, female, and married and single. So you could have done it manually also using a if-else function. But if you have many categories, it will become tedious to do. So we have a function to do that, to help us do that. Okay. Excuse me. So don't worry, these things will become clear. Just revise it once because this is something pretty new to you. So nothing difficult, but since it is new, it might take some time to digest. So just watch the recordings, or once I send the codes, already send the codes, just go through it once. I've given the comments, so I've written what you have to do, why you have to do. Okay. So it will make it clear. Okay, guys. So what did we do here? We took each of the categorical variables one at a time, and then we created dummy variables, right? And then we merged it with the original data set. What if somebody asks me, what if I have 10 categorical columns? I have 10 columns which are categories. So do I have to do this 10 times? So going by this code, it seems like we have to do it 10 times, right? Because I'm doing it one at a time. But that is not mandatory because I had to show you this point, so I made it twice. There is a function, the same function you can use for the entire data frame. So it will do for both the columns simultaneously. We will see that tomorrow. But right now you just understand that we have to create dummies for each column which is category. Okay, tomorrow we will see a function which will do it for all the columns at once. Okay, so let us move ahead now. Now we have our final data ready, right? Now we can run our linear regression where this is our dependent variable and all the others are independent variables. Okay, and now we no longer need these two columns because we have already created dummies for them. Now these two are not required. We can delete these two columns. Okay, so that is what I'm doing in the next step. Now we no longer need married and gender column. We will be using their dummies instead. Okay, because the dummies represent the same information, right? So this guy is male, so dummy is 1. This lady is a female. This is a lady, so this male is 0. So we already have captured this information in these two columns, last two columns. So these two columns are not required. So we will delete them. So deleting a data frame, if you remember from last week's code, it is data frame dot drop. Okay, and whichever columns you want to delete, and you give axis is equal to 1 because we are deleting columns. If you delete a row, it is axis is equal to 0. If you delete a column, it is axis is equal to 1. And data frame dot drop. So the same thing I am doing here. Okay. So after deleting, this is how my data frame looks like. Okay, this is my final data, which is ready for modeling now. Okay, clear guys? Everything clear till now? Okay, great. So just a minute, I'll come from the washroom. Okay, just 2 minutes. Okay guys, so everything clear till now, right? So we can move ahead now. Now let us move to the modeling stage. Okay. So in Python it is slightly different. Okay, so for example, now the modeling part, honestly, if I have to be honest with you guys, is simpler in R. Okay, it is easy to do modeling in R than in Python. Okay, the syntax is slightly tedious in Python. So in R, if you remember, it is pretty simple. You just write linear model, you write your dependent variable, then a tilde sign, and you write your independent variables, right? And then you write data is equal to the name of the data frame, right? This is what you do, and this is the name of your model, for example. Okay, pretty simple, straightforward, all in one line, done. Okay, in Python it is slightly tedious. Okay, so what you have to do in Python is, first you have to separate your dependent variable and your independent variable. You'll have to separate them. You'll have to mention that, let's say x1 is your dependent variable and x2, x3, x4, these are my independent variables. You'll have to specify, and then you can call them and then run a modeling. Okay, so let's see how we do that. Okay, so what we do, so this is what I'm done. Decide your regressor and your predictor variables. So regressor is nothing but the variable, the dependent variable. Okay, and predictor is nothing but the variables which you are using for prediction. So your independent variables. Okay, so from the above head command we can know that, okay, this is my dependent variable, and this, so age, account number I'll not be using because account number obviously will not determine that you will pay your loan or not. Okay, so age 1, years of experience 2, number of vehicles 3, male 4, single 5. 5 independent variables we have and 1 dependent variable. Okay, so what have I used? I have used age, number of vehicles, then this column M, and this column single. So all these columns I have taken as my independent variables, and notice that I have not taken years of experience, because we already saw that age and years of experience had 99% correlation. So I'm not taking both, I have just taken age. So if two variables have 99%, you can take any one of them. It wouldn't make a difference. You could have taken years of experience also, it would mean the same thing. Okay, because they are 99% same. So I have separated all the independent variables. So I have put them inside X. Okay, so X is a data frame which has only these variables. Similarly, I have separated the dependent variable, which is losses in thousands. I have put this inside Y. Okay, because I'm trying to find the equation, right? Y is equal to mx plus c. So I have separated the Y, I have separated the X now. Okay, now remember, we also split the data into train and test, right? So we'll be doing that in Python now. Okay, so how do we do that in Python? How did you do that in R? So there are many ways you can do that in R. Which one did you use? Anybody remembers? How do you split the data into train and test? Great, yeah, we use the split function for that. Paridhi, we don't use them together, because if we use them together, we'll be violating one of the assumptions of linear regression, right? We don't use age and number of years of experience together because we'll be violating the assumption of linear regression, which is that the independent variables should not be correlated. Okay, so that assumption will be violated. So we are not using both of it, and both are the same. So if you use it, it will create problems. So we use any one of it. Okay, yeah, we use sample.split in R. Let's see what we'll use in Python. So in Python, what do? We use a function called train test split. Okay, so very easy to remember. What are we trying to do? We are trying to split train and test data. So the function name is also train test split. Okay, now this function comes inside this package. Okay, the package name is sklearn. Sklearn is short for scikit-learn, and this is where all the machine learning algorithms are. Okay, so from sklearn.cross-validation we are importing this particular function. Okay, so we are not importing the entire library, we are just importing one function from the library. So that is why I have written .cross-validation import this. Okay, don't worry, this is just a syntax, nothing to understand here. You will remember it as you practice. Now what am I doing? Now this is the tricky part. Okay, here also this is just pure syntax, nothing to understand, but there is some hierarchy here. Okay, first you will always write the training data that you want. Okay, so let me go back. So after splitting your data, let's say this is your original data frame. Okay, this is your original data frame. You have your dependent variable here which you are calling x, and you have all the independent variables here which you are calling y. Now you have to divide the data into two parts, right? Train and test. Let's say you divided it here. This is your train and this is your test. But ideally, literally you divided your data into four parts. One is this. This is your 2. This is your 3. And this is your 4. So that's what we do. We first write, let me see the order in which I have written. Okay. So we first write x train. Okay, that means this part. This is our training data, our dependent variable of train. Then we write x test. Okay, so we are referring to this as the second one here, and it should be in this order only. Okay, don't get the order wrong. It should always be in this order. 1, 2, 3, 4. Then you write y train. Sorry, I missed this, so I made some mistake here. So this will be your, this is your y. This should be your y actually. Y is only one, x's are multiples. So this is your y, these are your x's. Okay. So x train, that means this is your 1. X test, this is your 2. Then you have 3 and you have 4. Okay. Y train and then you have y test. So it should be in this order always. You will have to remember this. Okay. There is no other way. So you can, or you just Google, you will get this code. So you will remember with practice. As you practice, you will remember that we first write x train, then we write x test, and so on. Okay. Am I not audible, guys? Can you hear me? Okay, Paridhi, others can hear me. Okay, so Praveen has a question. Praveen is asking, okay, we have a lot of questions, so let me start from the beginning. So Praveen has asked, do we have to choose significant variables manually unlike our? No, of course not, Praveen. So you can start by selecting all the variables, and then from the p-values we can determine which are significant. Okay. You can start off with all the variables and then we can determine, just like in R. So these processes are just like in ours, just the syntax is slightly different. Otherwise it's the same. Praveen has another question. What if we have 100 variables? Then how do we decide which ones to take? Yeah, Praveen, I'll come to that question. So this is a question which you should have clarified in R as well. So not sure why didn't, but yeah, I will try to answer. If you have 100 variables, how do you decide which variables are important, which are not? Okay. So let's get, so what I have done here is I have divided the data into train and test. Okay. So I have used the function train test split. The inputs it takes is first the x. The x is nothing but what you have given here. Okay. So these are pure syntax things. Okay, guys, just you'll have to memorize this syntax or you'll have to Google to use it. There's nothing to understand here. Then you have your y. Y is nothing but your dependent variable, and then you write what is your test size, how much test size do you want. So I want 30% in my test data. Remember, this is what you used to give in your R also, sample.split, you used to give split ratio, right? There you used to give how much data you want in your training data. That is why you used to give 70% and 60%. But here we give the opposite, how much data we want in the test data. Okay, so I'm giving the test data size is 0.3. That means 30% I want in my test data. And you give a random state here itself. So in R, you first set the random seed and then you proceed, right? Here you give the random state variable here itself. Okay, clear guys? Is this clear? I hope you understand why do we set a random seed, right? Okay. Okay, Amrachi, he doesn't understand. Okay, so let me explain. Okay guys, why do we set a random number? What is, oops. I like the green color. So for example, in R you do set.seed, right? And you write some constant here. And in Python we write random underscore state and you write some constant here. Why do we do this? Let's say we have this data. Okay, you have many rows here, thousands of rows and some columns. Now when you split your data into train and test, we split it randomly, right? That everybody knows, we split it randomly. So 70% of the data comes in train and 30% let's say comes in test. Now if we do it randomly, row 1 may go in train or test, right? It has 70% probability of going into train and 30% probability of going in test. Okay, let's say you run this, you get some result. Okay, but when you run it again, what happens? Row 1 initially, when you ran it for the first time, row 1 went into train. When you run it again, row 1 might go into test this time. So your results will vary because of that. Because different rows are going into train and different rows are going into test, the results will slightly vary. Not a lot, but it might slightly vary. So to avoid that, we set a random seed. If you set a random seed, that will not happen. Row 1 will always go in the same either train or test all the time. Okay, so the split will be common across. Or let's say if person A is running and person B is running, so he will get a different training data, B will get a different training data. But if they set a random seed, both will get the same training data. Okay, that is why we set the random seed. Clear now, Amrachi? Yes, exactly, Rajesh. It is equivalent to set.seed in R. Any number, who said you have to set it to 1? You set it to any number. Now if I choose 1000, you will ask me why did you choose 1000? So I have to select one number, right? So I chose 1. 1 is my favorite number, by the way. Yep. Okay, so you choose your favorite number. Any constant, it has to be a constant, that's it. Okay, so I have done that. So now my split is done. So I have all my training data, all my dependent variables of training data, I have it in Y train. I have all my independent variable of training data into X train. Okay, now I'm ready for model building now. Now for model building, I will use a function which is known as linear regression. So we are doing linear regression. The function name is also linear regression. And this comes from this package. Okay, don't worry about these. You will remember slowly with practice. So even I forget sometimes. So I just Google and find it out. Okay. So sklearn, again sklearn package, dot linear model. Okay, dot linear model, import linear regression. So I've imported this function now. Now after that, this is how you call the function. Okay, first you call the function. So I'll call the function using, so lm is my object now where I have called this function. So this function I have called. Now I will pass my training data to my linear regression function. Now linear regression function is in this object, right? So I will just fit the model there. So how do we do that? lm.fit. So these are pure syntaxes, okay guys. So lm.fit, I will write the x variable first, the independent variables, and then I will write the dependent variable. Okay, so this is all, my modeling is done. I have fit the model. So this concludes your modeling portion. How do you do modeling in Python? Okay, Clear, guys? I know the syntax will take time for you to understand. There's nothing to understand basically. It's just the syntax. Okay. There's no concept involved there. It's just the way you write the codes. So you will have to basically memorize it. And the concepts you already know. What linear regression is, how does it work. So all those things are already clear to you. I'll explain it briefly. But this is how the syntax looks like. Okay. So in R you use the tilde symbol. Here we divide the data into 4 parts: X train, Y train, X test, Y test. And then we fit the model on the training data. And that is all. So we are yet to predict. Okay. We haven't made a prediction yet. We have just fitted the model on the training data. So if you see, I haven't used the test data yet. Okay. So now what will I do? To get the equation of the line. So linear regression is basically fitting a straight line, correct? Fitting a straight line in the data. So to get the straight line now, I will need the intercept of the line. I will need the coefficient of each of the variables that I used, correct? So all the betas I need, beta naught and beta 1, beta 2 and so on. So how will I get that? These are the functions used for that, okay? So this is a function which is used to get the intercept. Where is this LM coming from? LM is coming from this object that I created earlier, okay? So LM is my linear regression object, right? It will have all the values. So this intercept is a function, okay, to see the intercept. Similarly, LM dot coefficient is the function to see the coefficients, okay? So if I run this, this is what I get. So 539 is the intercept, okay, because I'm printing the intercept first. So the intercept is coming here. Then I'm getting these as the coefficients. Paridhi, you always build your model on the training data and never on the test data. Okay. Yeah, I will talk about it. Just a minute, okay? Let me finish this and then I will talk about it. Why don't we? Okay, Amrachi, yes, I will talk about it. Okay. Okay. So I think your concepts are not very clear in linear regression. Let me quickly revise. Okay. Let's say we have this data. Okay. Let's say we have income on y-axis. This is our y variable. Okay. This is what we are trying to predict. This is our dependent variable, and I'm taking just one independent variable, which is age. Okay. Let's say I have a person whose age is, let's say this is 5, 10, 15, 30, 20. This is 20, this is 25. Okay. So I have people of 4 ages and I have some income. So this guy, his age is 20 years and his income is, let's say, 100,000. This is 110,000. This is 200,000. This is 210,000. Okay. Just some random points. And let's say this guy, I have a guy here who is 25 years old and his income is 110. I have another guy who is 30 years old. His income is also 210. I have another guy who is 30 and his income is somewhere in the middle of 205 and points like this. Okay. So I have a few points like this. Now linear regression, what do we do in linear regression? In linear regression, we try to fit a line which minimizes the sum of squared error. Okay, we try to fit a line. Let's say this is the line. We try to fit it in such a way so that the sum of squared error is minimum. Okay, we try to minimize this quantity. We try to minimize this quantity, and for this we use an algorithm which is known as OLS. Okay, ordinary least squares. Okay. Now what is this SSE? SSE is nothing but y predicted minus y actual whole square. Okay, and you sum it over all the points. Okay. Now what is y predicted? You predict what comes on the line because you use a line to predict, right? So beta naught. Okay, let me take some values because I have some example here, right? So let's say it is 5 plus 10 into age. This is our equation. Okay. So if your age is 20, if your this is your predicted values. Okay, this is y hat, not your actual value. Actual value is y, but what we are predicting is y hat. Okay, so how will we determine what is the value of y hat? We just fill the value of age and we get y hat. So let's say if somebody's age is 20, so what will we get? We will get 20 into 10, which is 200, and plus 5, so we will get 205. Okay, so that means we will predict somewhere here. Okay, so don't worry about the line. The line is not matching with the one which I have drawn. The equation is not matching. So the equation probably will be something like this. Five into age plus, let's say, 1.2. Something like this, you'll have the equation. So when you put the age as 20, you will get 20 into 5 is 100 plus 1.2. So 101.2. Okay. So the actual income here was 100, but we predicted slightly more. We always predict on this line. Okay. Whatever predictions we make always lies on the line. So for example, in this case, we are predicting this green color. In this case, we are predicting this, and so on. So if somebody is 20 years old, 20 into 5 is 100 plus 1.2, it gives 101.2. So this green point. So what is the error? What is the error we made here? So the actual value is 100, but what we predicted, this is coming from here, we predicted 101.2. So this whole square, okay, this equation I'm writing, okay, plus similarly for this point now. Now for this point, the actual value was close to this, but what are we predicting? We are predicting this. So we will have some error here also. We'll take that square also, and so on. For each of the points, we will take these squares, and finally we will minimize that. And once you do that, you will get the equation of the line. You will get y equals to sum beta naught plus beta 1 into age. Okay, this is how you get the values of beta naught and beta 1. Now what is this beta naught? The beta naught is nothing but where your line intersects the y-axis. So this is where it is intersecting, right? So this distance is known as beta naught. Okay, and what is beta 1? Beta 1 is nothing but your slope of the line. So slope is nothing but beta naught is delta y by delta x. Okay, your rise over your run. Guys, are you getting this? Amrachi, is it clear now? Okay, great. So in the example, okay, Amrachi has a question. So can intercept here mean the regression line that minimizes error? No, the intercept doesn't mean that. The entire line is what it does. Okay, the entire line tries to minimize the sum of squared error. Okay, that is how you get the line. Okay, so to put it in a slightly detailed way, if I have to put it in a slightly detailed way, so what are we trying to minimize? We are trying to minimize y actual minus y predicted whole square, right? This is what we are trying to minimize. So how do we minimize this? Again, let me write the same is equal to what is our y predicted. So y actual, I'll just write it as y predicted is y hat, let's say, okay, whole square. We are trying to minimize this. If I again write it, y actual is y actual. Y predicted is nothing but beta naught plus beta 1 into x. Let's say we have only one x. Okay, I'm taking only one independent variable. So this is what we are trying to minimize, right? So let's say this is y. Okay, now how do you minimize a function? High school mathematics. How do you minimize a function? We differentiate it and we make it 0, and then we solve this equation, right? And then we get some value of x. At that value of x, this function y will be minimum. So that is what we will be doing here. Okay, so we will differentiate it with respect to beta naught and with respect to beta 1. Again, this is going slightly more into the mathematics. This much is not required, but just if you want to know. Okay, so we will do a partial differentiation. You would have learned it in school, right? You will do a partial differentiation of this line, of this equation, with respect to beta naught and beta 1, because these are our variables which we want to find, right? X is not a variable. We already know the value of X. We want to find what is our beta naught and what is our beta 1. So we will differentiate this entire thing with respect to beta naught and then with respect to beta 1, and then finally we will get some value of beta naught, we will get some value of beta 1. So that is how beta naught and beta 1 are found. Okay, that is how the algorithm does it. So this entire algorithm is known as ordinary least square. Hope this is clear. Okay guys, so don't worry about that much of mathematics. It will come with time. So slowly, first understand the basics, and then maybe you can jump to those detailed mathematics within the models. Okay. So that is what I have done now. So I'm just printing the values of intercept, and I'm printing the values of the coefficients of the variables. Okay. So how many variables had I used? I had used 4 variables, right? Age, number of vehicles, gender, and single. So I should get 4 coefficients, and that is what I'm getting. In the same order, I'm getting 4 coefficients. Okay. Okay. And then what I'm trying to do? Then I'm making a prediction. Okay. After this, I'm making a prediction. So prediction is similar as we do in R. We use the predict function. So same LM model. My model name is LM. So LM.predict I use. LM.predict, and then I gave on which data do you want to predict? I want to predict on the test data. And while predicting on test data, you just need the independent variables, not the dependent variable, right? For building the model, you need both dependent and independent. But for predicting, you just need the independent variable. So I'm passing only the independent variable. So this is what now my predictions are in this object called pred. And then again, I use a R square score. You remember R square from your R classes, right? Same R square we will try to calculate. So the function name is R square underscore score, which comes from this package. We will just use this. We will give the actual value and we will give the predicted values. Okay, so this is our actual value, this is our predicted value, and then I'm just printing this absolute error. So mean absolute error is what I'm printing, and this is the value of it. So 0.295 is the mean absolute error. Okay. Yes, Amrachi, what is the relevance of coefficients here? We can discuss that. Okay. So what is the relevance of coefficients? So as I told you, the coefficients represents the rise over run, right? I told you, right? If this is the line, beta is equal to beta 1 is equal to delta y divided by delta x. Okay. So coefficients tell you that if you increase your x by 1 unit, by what amount will your y increase? Okay. So for example, if this is my line, if my x is 1, what is my y? 8, right? If my x is 2, what is my y? 11, right? So we don't have to calculate this. You directly get it from 3. So it increased by 3 units, right? So that is what this tells you. That if you increase x by 1, by how much will your y increase? It will increase by this amount. So this is nothing but your beta. This is the coefficient. So this is what it tells you. Okay? Clear? Okay. So that is what I did. I just built a model and I made a prediction. And after prediction, what do? You calculate your error matrix, right? You calculate your R square and all. So the R square you see here is pretty low. So R square I'm getting is 0.29 only. Okay, this is the R square. Okay. So I'm getting a very bad R square, not a good one, but okay, again, the R square depends on the data. This data was not particularly good. So I'm getting R square of very small value, only 0.29 I'm getting. Okay, so let me run this once. Oops. Okay, I did not run the previous lines, so I'll have to go back from here, I think. Okay, this is still running. Okay, so here it is. So this is what I got. This is my coefficient. This is my intercept, and these are my coefficients. 148 is my. So this is my intercept. I'm printing first, then I'm printing this. Okay, R square I'm not printing. So I'll have to write a print statement here to print it. And I'm printing the mean absolute error, right? So I'll get 4 values now. So 0.29 is my R square and my absolute error is 148. Okay, that is my absolute error. So on an average, I'm wrong by 148 thousandths, okay, because my dependent variable was in thousands. So if the actual value of your loan default amount is $1,000, I will be off by another $148. So if it is 1,000 actual value, I will predict 1,148 and so on. Okay. So is it clear till now, guys? Okay, great. So just let's take 15 minutes break. I'm tired of talking, so I need a break. So let us quickly take and then we will answer Amrachi's question. Yes, Amrachi, you can always label the outputs. You mean the print, whatever we are printing, right? You mean whatever we are printing, right? Yes, yes, of course. You can add some labels. So you can just write things like, for example, here. So you can write print and you can add something that the R square is something like that. You can do. Okay. I did not do that because I'm lazy. No, here you cannot do. You cannot add the labels here. It will come in this format only. And you'll have to basically go back and see in which order did you give the variables. And then you can do. Or you'll have to use a loop for that. You can use a loop and then one by one you can print. Okay. So guys, let's take a 15 minutes break. Okay. Yeah, I too need a break. I'm tired of talking. Okay, so let's meet at 2:10 or 2:15. Let's meet at 2:15. Okay. Okay guys, see you then. I'm back. Yeah, Paridhi, I will answer your question now. And I think somebody else had asked, how do we decide if we have hundreds of variables, right? I think it was Praveen. So I'll answer those questions as well. You guys are here? Okay. Okay, I was preparing lunch. So my lunch is almost done. I just have to keep all the vegetables I have cut. I just have to keep it on the stove now. And it will be done. So really hungry. And I have another class from 4 o'clock. Okay. So at 3 the class ends and I have another class from 4. Yeah, Paridhi, I know how to cook. So I have been staying alone for almost 3 years now, 3.5 years. So I have learned how to cook. You can't afford to cook to have outside food every day, right? I mostly cook like I eat to live. I don't live to eat. So what I prepare is not something which is very tasty. But yeah, I somehow survive on that. So I mostly prepare khichdi, if you guys know what khichdi is. I mostly prepare that. And of course you don't need to be a chef to prepare khichdi, right? Yeah, Maggie. So this is what I mostly prepare, but I'm a little health freak, so I try to avoid food like Maggie, and also I prepare khichdi, but I prepare it with brown rice. So brown rice is healthy, right? So I prepare it with brown rice, and I try to add some vegetables there so that I'll get all the fiber content also. No, my friends make fun of me. You too can, but yeah, that is how I am. Okay, so I guess everybody is here, so we can start. Okay, so yeah, so Paridhi asked the question. Okay, that why do we use the train data for model fitting and not the test data? Okay, so let me open up a page and then answer the question. Okay, so let's say we have this data. Okay, this is our entire data set where we have a dependent variable, which is our y, and we have all the independent variables here, x1, x2, and so on. Okay, now we divide the data into two parts. Okay, imagine this is a straight line. Okay, this is our train and this is our test. Now Paridhi asked me, why do we always take the train data to build our model? Okay, so see, we have to build. So let me break the question into even simpler question, which is why do we even break the data into two parts? Why do we do that? Why can't we use the entire data frame and then build a model on that? Okay, why don't we do that? So why don't we do that is because, see, just a lame example. Let me give you a lame example. Okay. Um, yeah, let me give you a lame example. So let's say we have, this is 2010, 2011, 2012, dot, 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 and we are in 2017 now. Okay, and we have 18 and we have 2020 here. Okay, let's say I give you some data. Let's say India's gross domestic product. Okay, let's say it is something like this. We have data till 2017. Okay, obviously 18 and 20, 18 and 19 we do not have. So now let's say I ask you to build a model which will predict, or imagine this is India's population. Why to go into complex parameters like GDP? Let's say this is population of the country and these are the years. Okay, yeah, some numbers. Okay, so it is increasing in this way. Now in 2017 we are here. Okay, we are close to 130 crores or 1.3 billion crores. Amrachi will not understand crores. That's an Indian way of measuring. But yeah, Amrachi, we are a nation of 1.3 billion people. Okay. Yeah, might surprise you. Yeah. Okay. So now let's say we want to predict the population of India in 2018 and 19. So how do we do that? So we build a model. Okay. We take this data. Let's say we take the entire data. I'm not dividing the data into train and test. Okay. I'm taking all the data and I built a model. Now I have a model. Okay. Let's say I have a model which is, let's say, f of x. X is year here, right? Now, how do I know whether this model is good or not? What do I do to know that? So what I'll do, I'll predict. I'll predict for these variables only, right? For these years only, I will predict. But the model has already seen 2010 data, 2011 data, and all these data. So the model will generally do good in these years because the model has already seen these years. So the model will do good in this. Okay. But the actual test of a model is when the model does good on new data, which it has not seen before, on the future data. Okay, for example, yeah, so let me give you that example. So let's say we build a self-driving car. Okay, we build a self-driving car. It works pretty well. So obviously we cannot test the car straight away on Indian roads, right? So what we will do, we will first have an enclosed space. Okay, let's say within some university campus, or let's say in an open area. In an open area where there are no people around, we will test the car here, right? Now, once you have tested it here, what do you do? Do you directly put the car into production and let people buy and drive it on Indian roads? Obviously, it's a self-driving car, so they won't drive it, but they will be seated at the back. Do you want that to happen? No, right? It was tested in a particular condition where there was no traffic around. So it has to be tested again in actual condition where we will have traffic. Only if it performs well there, you will basically clear that yeah, the car is good, it performs well on actual condition, and then you will put it into production, right? So that is why we split the data into two parts. One is the training part, one is the test part. The test part is where the model does not know what is there in the test part. The model has no idea. And without having any idea, if it still performs well there, that means the model is pretty good. So that means here what we will do, we will not include the entire data set to build a model to predict the population of India. Okay, we will say till, let's say, 2015. Till 2015 we will consider the data. 2016 and 2017 we will consider as test data. Okay, we will build a model on this and then we will apply the model on these 2 years. Okay, now if the model, these data the model has never seen before, this is totally new to the model. Okay, now after applying the model on this data, after fitting the model till 2015, we will have our equation ready. So let's say we get this equation. Now this equation is frozen, we are not changing it. Okay, this is frozen now. Now we apply this equation on this data and then calculate the value of errors. If that errors is pretty small, we say that yes, the model is good. It is doing good on new data, on the future data, because whatever we get in the future will be equivalent, right? Since the model has not seen this before, the model has not seen this before also. So it will be similar. So if the model performs good here, we can safely assume that the model will perform good in the next year also. But obviously there is a caveat there. If the macroeconomic scenarios change, obviously it will not perform good. But all the things remaining similar, the model will perform good on the future data also. That is why we split the data into train and test part. Now did I answer your question, Paridhi? Okay, now you may ask another question can be, why do we split into 70-30, or why do we give more proportion in training data and less in test data? That is because more the data, the better it is for the model. Okay, So if we give only, let's say 30% to train the model will not see a lot of data. So I can't take just 2010 and 11 and 12 and build a model to predict the population and ask it to predict for all these years. The model will not be good, right? It needs more data to learn. So I will give more data for it to learn. So we generally do it in 70-30. So that 70% of the data is used by the model to learn, and only 30% remains, which we can use for testing. Okay, that is why we divide the data into train and test, and in that ratio. Okay, so now another question somebody asked me, what if we have thousands of variables? How do we run a linear regression? How do we decide which variable is important? This is a very good question, and this is a difficult question actually. So let's say you have x1, x2, and you have, let's say, x100. Now how will you decide which variables are important, which are not? You can't, if I write in R language, you can't just write dependent and you can't write everything here, right? So how do you know which is important? So we decide from the p-value. Okay, we will get p-values, right? On the p-values we decide. If we have p-values less than 0.05, that means this variable is important. Okay, p-values less than 0.05 or sometimes even 0.10. So this means it is very good. Less than this means it is good. Okay, it is also denoted by stars in R, if you remember. But Python, you will not get stars. You will just get the p-values. So from the p-values, we will determine whether the variable is important or not. Is it clear now, guys? Guys, please respond. Okay. Okay, so let us move where we stopped. Okay, so we found the mean absolute error, and this was the value. So obviously, smaller the value of error, the better it is. So now we found that the R square was 0.29. So 0.29, is it a good R square or is it a bad R square? Yeah, it is not. We cannot say it is bad because it depends on data. Okay, so honestly, in the industry, when you run linear regression, the industry data is usually uh, very dirty and will have a lot of noise. So sometimes it depends on the data. You can easily get 80.8 R square sometimes, and sometimes even to get R square of 0.4, you have to struggle a lot. So it all depends on the data. But yeah, on an absolute value, if you see R square closer to 1, as you guys are telling, R square closer to 1 is basically better. Okay, Sharmin is asking, how do you determine p-values? Sharmin, the p-value comes from a hypothesis test. Okay, that is pure statistics, which is out of scope of this course. Okay, I would have covered that if I had taken your R session. I usually cover that when we take R, because you have more time given in the R session, right? Python is just 5 days, and in 5 days I have to cover Python as a language and as a like for machine learning also. So it is not possible to cover hypothesis test here. Yes, that's what I'm telling. How do you determine the p-value? It comes from hypothesis test. Okay. In Python, yes, we will come to that. I'm yet to reach there. Okay. So yeah, so ideally R square value close to 1 is good. So let's see if we can improve the R square. Okay, we are getting 0.29, and now we will try to do something and improve the value of R square. Before that, I have just written the equation of the line. So linear regression means equation of a line. So if this is your intercept and these are your coefficients, your equation of the line will look something like this. Okay, so your dependent variable was loss in 1000. So the value will look like loss in 1000 is equal to 539.65, which is your intercept, minus 6.14 into age. Okay, so this corresponds to age here. Okay, in the same order. So age minus 1.79 into number of vehicles plus 97 into male plus 136 into single. Okay, this is the final equation of the line that we are getting. Okay, so now what does this mean? What is the interpretation? The interpretation is age has a negative sign of coefficient and number of vehicles has a negative sign of coefficient. Okay, so what does this mean? Who can tell me? What do negative sign in coefficient and positive sign in coefficient mean? Yes, guys, please respond. Yes, Rajesh, you are right. So negative sign means as you increase the value of that variable, your dependent variable will decrease. Yes, yes. So all of you are right. So if I have a negative sign of -5, let's say, that means if you increase that variable, your dependent variable will decrease by 5 units. Okay. If it is positive, it increases directly proportional. If it is negative, it is inversely proportional. Okay. That is what it means. So what do we infer now from this analysis? We infer that if your age is more, you are more likely to default. Okay. This is what it is telling us. So it is contrary to what we believe. Okay. Because okay, no, sorry, it is similar to our belief that if your age is more, the losses will be less. So we are talking about the losses, right? So if your age is more, you have less chances of defaulting by a lesser amount. Okay. Similarly, if you have more vehicles, the loss amount will be less, and that makes sense also, right? If you have more vehicles, obviously you will repay your loans. Okay. And single has a positive. That means if you are single, you will default by a larger amount. Okay, that is why it has a positive sign. Similarly, male has a positive sign. That means if you are a male, you will default by a larger amount. Okay, so it makes sense, and it agrees to what we found earlier using the box plots, right? This is what we concluded from the box plot also, that single people are defaulting by a larger amount, and this is what this is telling me. Single has a positive coefficient, and same for male also. Okay, guys, agree with this? Okay. Okay, now let us see. Now Sharmin asked, how do we get p-values in Python, right? Because till now we did not see the output, right? So to get the p-values, it's a little tedious. You'll have to run these few lines of code. So nothing to explain there. These are the syntaxes. You import these functions from these packages, and basically these few lines you have to run. So this OLS is a function which comes from this package. You have to run this line. Training data and the dependent variable you will have to pass, fit the values, and then you click on p values. And then this is how you get the p values. Okay. Or you can run lm2. lm2 is nothing but coming from here, this object, and you run a summary of this, and this is what you get. So this output is similar to how you get in R. Okay. So these are the coefficients, and these are the p-values. So you see almost all the variables has very small p-values except number of vehicles. So except number of vehicles, all the other variables are important, and so we should include them in our model. Number of vehicles, maybe you can delete this vehicle. Okay. So this is how you find the p-value. So nothing to explain here, just some syntaxes. So you will have to basically remember this or get it from Google. And once you have this, you already know how to evaluate based on p-value. So smaller p-value, the better it is. We look for values less than 0.10. Okay. So except number of vehicles, which is 0.4, 40%. All others are less than 10%. So we will consider all the others. Any doubts, guys, so far? I know these things, the syntax might be new, but don't worry about the syntax. You will get it. So that comes with practice. You will not get it in a day or something, and there's nothing to explain there. It is just pure syntax where you give some inputs and you get the output. Okay, so Rajesh is asking, how do we do diagnostic plots in Python? Yes, we will see that, Rajesh. So still a lot of codes is remaining, so we will see that. Anything else, guys? Did you receive the files which I sent you? Okay. Okay. So let us move ahead and see what else I have got. So what I'm trying to do now, let us try to improve the model. Okay. We got 0.29 as the r square, and let us see if we can improve. So what did we see when we took a histogram of the dependent variable? This is the histogram of the dependent variable, right? We saw that it has a right tail. We also talked about it, what is right tail and right skewed, right? So what we can do in these cases, whenever, because linear regression assumes, one of the assumptions of linear regression is that the variable should be normally distributed. Okay. So, but this variable is not normally distributed. So what happens in these cases when you have a tail towards the right side, if you take the log, it tends to become more uniform. Okay. Okay. So if you take a log of this, it will become more towards uniform. So that is what I'm trying to do now. I'm just trying to take a log of it. So here I have take a log of the dependent variable. Okay. And additional thing I'm doing. So you saw this pattern in the data, right? You saw this pattern, right? We see that some people have, like, a lot of people have less than 10 years of experience, and a lot of people have more than 40 years of experience, and there are very few who fall in between. So what I'm doing, I'm just creating a bucket here. Bucket means converting a continuous variable. This is a continuous variable, right? Years of experience. I'm trying to convert this to a categorical variable. So what I will do, I will create a variable which will be 1 if the value of years of experience is less than 10. I'll create another variable which will be 1 if it is between this, and another variable which will be 1 if it is above this. Okay. So let's see how do I do that. So here is what I have explained, what I have done. Okay. First, I have taken log of the dependent variable. That is pretty simple, nothing much there. Why did I do that? Because my dependent variable was not normally distributed. That is why I'm doing that. Okay. Now create a new categorical variable. I'm calling it age category, which is young if the person is less than 28 years old, which is middle aged if the person is between 28 and 58, and if the person is old, if the age is greater than 58, I'm calling it old. Okay. So did you understand what I am trying to do here? Sharmin, because as I said, the variable is not normally distributed. Okay. So we try to make the variable normally distributed, and log works most of the time. Okay. When you take log of something, it becomes normally distributed. Okay. And then we created a categorical variable from the continuous variable, which is age or years of experience. Okay. I have created it from age. So this is how I created. I basically used a comprehension for it. Remember comprehension, we had learned it. So if you use comprehension, you can do it in one line, one single line, you can do that. So that's the advantage of using comprehension. So I created df. This is my new df, new data frame, where I have created a variable called age category. Okay. And I am writing it young if age is less than 28, else middle aged if age is between 28 and 58, else old, otherwise if both these conditions are not satisfied, it is old. Okay. For I in range, so it starts from the 0th index till the last index. So this is just pure syntax, and I'm taking a log of the dependent. I'm using math.log. Okay. So the log comes from this package called math, and I have used another function called map for this. Okay. So don't worry, this is just a complex function to do that. So using the map function, I'm taking the log of this entire variable. Okay. And then what I'm doing, since the variable that I created is again a categorical variable, I'll have to recreate the dummies for this categorical variable, right? So that is what I have done. I have again used pd.getDummies. I'm recreating dummies for the new categorical variable, and this is what I have finally. Okay. So this is the variable I was talking about, age category. So it is young, middle aged, and young and old. Okay, depending on the value. Okay, so after creating the dummy, it will look something like this. So instead of age category, I will have old and young. So see, this has three categories, right? Old, middle age, and young. I have two dummy variables for it. One is old, one is young. Each has 1 or 0. And this is the dependent variable. I just took the log of it. Okay. Then I will repeat the same procedure. I will again create my X. I'll again create my Y. I'll again split the data into two parts. Okay. And then finally, I'm rerunning the model again. All the same codes will be repeated. And now you see the R square improved to 39%. Sorry, 42%. R square improved to 42%. Earlier it was 29%. So from 29% we went all the way till 42%. So this is one of the ways which you can use to improve your R square. Okay. So we reached 42%, and these are the intercepts and these are the new coefficients that you see. So your final equation will be something like this now. Now you will have log of losses instead of the losses. So if you want the losses in thousands, you take an anti-log of it again. 0.39 is without considering, okay, let me see, print. Okay, 0.39 is the R square, sorry. 0.39 is the R square and 42% is the absolute error. Okay. So 42% is the absolute error and 0.39 is the R square. So we improved from 0.29 to 0.39. So around 10% is what we improved. But still better than before, right? Jagdish, the plot of revised model. Okay, I'll have to see the plot here will be difficult because we do not have just one dimension, right? We have multiple dimensions here. So I will not be able to show you a plot. I can show you the plot if we are dealing with one dimension, so that I will have your independent variable on the x-axis and the dependent variable on the y-axis. But since we have more than one dimension, we have age, we have the category, gender, we have married, marital status, then the new variable that I created. I don't think I'll be able to create a plot for this in 2 dimension. Yes, so Swati is asking log y, she understands why log y has improved the model, right? But she does not understand, or she fails to understand why conversion of her continuous to a categorical help the model. Okay, let us see. Okay, so let me so if you remember, this is what we had, right? Our histogram looked like this for years of, or for age, right? This is how the histogram looked like. We had a lot of people who were below 25 years old, and we had a lot of people who were above 45 years old, but we had very few here, right? This is what the frequency tells you, right? This is the frequency. So now how does it help? See, any model, what it tries to do, any model, it tries to identify patterns from the data, right? So here, see, there is a pattern here that a lot of people are below 25 and a lot of people are above 45. Okay, but if it is a continuous variable, you will have thousands of values here, right? You have so many values here that sometimes the model gets confused. It fails to identify this particular 25 value. Okay, it fails to identify. Similarly, it fails to identify this particular 45 because you have so many values around this. Okay, so it is not very apparent for the model to catch this pattern in data. Now when you convert this to a categorical variable, what do? You create two variables, right? Let's say variable 1, you create variable 2. Variable 1 is 1 when your points lie in this region. So this is 1, this will be 0. Now when the points lie in this region, when your points lie in this region, this will be 1 and this will be 0. Now you are setting a clear demarcation that if it is below this, I am 0. If I am above this, I am 1. So the model will not get confused. Now there is a clear demarcation. But earlier, how did it look? It looked 44 and it looked 46 here. So the model was getting confused because the values ranged from 13 till, I don't know, 80, because the starting value was 13 and it went all the way till 80. So when you have a huge distribution like this, 13 till 80, and you have thousands of points lying here, it becomes very difficult for the model to demarcate like this, that something is greater than this, something is less than this. But when you set it to a categorical variable like this, ones and zeros, the model can easily distinguish that, okay, I'm 1 here and I'm 0 otherwise. So it becomes easier for the model. That is why this helps your model building process. I know this is a little difficult to understand, but think about it. Did it help, Swati? Yes, you can say that is true, but you should have less number of categories. You should not have maybe more than 8 or 10 categories. You should have a fewer number of categories, okay? And you should have data points in each category. It should not be that 80% of your data is in one category and the remaining 3 or 4 categories has only 20% of the data. Because again, it needs more data points to identify the pattern, okay? And this process is known as feature engineering, okay? The process of creating new variables from existing variables is known as feature engineering. So for example, we created log y from y, right? And we created a categorical variable from a continuous variable. So these processes where you create new variables using existing variables are known as feature engineering. Okay. Yes, Ayushi. So Ayushi is asking, how do we come to a conclusion that this is the best possible model? Of course, Ayushi, there is always a scope of improvement. So we can try other things on this model. So for example, so right now the feature engineering that I did, I just used one column to do feature engineering, right? I just took log y for y and I created a categorical from a continuous. Sometimes you use two variables or more than two variables to do feature engineering. So let's say, for example, I can combine all the married males together and I can combine all the bachelor males together. Okay, something like that I can do. I can create a new categorical variable which is 1 if it is male and if he is bachelor, otherwise 0. Similarly, I can create a categorical variable which will be equal to 1 if it is a female and if she is a bachelor, if she is a bachelor. Okay, so you can try those combinations. I did not try that, but there is always a scope of improvement. So you can try doing such stuff. It may help, it may not help. So you do not know basically. So this is the tough part of machine learning. Okay, this is the tough part of analytics. You never know that you have achieved the best that you can. So you should always keep trying. So obviously, if in the industry you will have time limitations, so you cannot do that. But with experience, this comes with experience. As you go on working on different kinds of data, different kinds of model, the more you study, the more ideas you get, and you start implementing the ideas. Okay, so this is how it works. There is no one answer to that you apply this and you achieve the best model. If it was so easy, everybody would be doing it, right? But it's not so easy. So you get to learn all of this with experience. So Amraji is asking, at what stage are we now? The training module or the testing? Amraji, we built a model on the training data and then we applied it on the test data. We basically made prediction for this, and then on the test data we tested the accuracy of the model. So we got to know. So you see here, right? This is what we have done. So we have applied it on the test data. So this is the test data that we have passed, and then we are calculating the absolute error on the test data. So this is the error that we are getting on the test data. Let's say if you are okay with this model, if you are happy with this model, then this is the error your model is making. You can submit this report to your client. And if the client is also okay, he will accept the model, or he will say that no, I'm not happy with this R square and such high error, so I want you to build a better model. Then you should try some other combinations and try to build a better model. But otherwise, this is how it ends basically. But there will be multiple iterations like this. Anyway, in ideal scenario, you won't have just 4 columns. We had just 4 columns here, right? You will have other columns also. So you can utilize all the other columns also. Okay, guys. So I'm done from my side. You guys tell me if you have any doubts. We have 10 minutes, so we can discuss any doubts that you have. So just go through this data set one. I know we covered a lot today, a lot of new things for you guys. But try to revise, try to watch the videos, any portion where you have a doubt, try to just see the video again, the recordings again, and see if that helps you. You can pause the recording and then replay if you want, and see if that helps. Otherwise, we can always take up your questions tomorrow at the beginning of the class. Okay. So guys, where are you? I'm not getting a response. Are you there, or everybody has slept on a lazy Saturday afternoon? Amrachi, on this data set, getting 0.9 will be next to impossible. Okay, I tried some things here, but this data is not pretty good. Okay, so I don't think you can try things on your own, but this data is probably very noisy, and getting good R square is difficult here. Okay, so you guys can take this data and take it to R if you are comfortable with R. Try it in Python as well. And it doesn't matter which language you try, it will give the same R square in both places. Okay. Okay, so Rajesh is asking about the diagnostic plot. No, Rajesh, we do not have such plots in Python. So you'll have to manually create plots like that. Okay. As far as I know, there are no direct functions. Yes, in R it is pretty simple. You plot the model and you get the 4 plots that you're talking about. But here it is slightly difficult. You'll have to plot it one at a time. Sharmin, I already told about it, right? You can create a new variable which will be 1 if it is a male and if he is bachelor, and it is 0 otherwise. Similarly for female and bachelor, that way you can try creating combinations and feeding into the model. It might help. Jagdish, I have already shared the script with you. Have you guys got the script? Okay. Yeah, I have shared. Others have got. What is the source of your data? No, Amrachi, this data has been taken from the internet. So I don't think this is real life data set, because real life you won't have just 4 columns. But maybe this is generated data, but not randomly generated, because it does have some pattern, right? If you randomly generate data, you won't see any pattern. So maybe it was taken from a bank, but they have filtered out most of the columns. So I'm not sure, because I was given this data by Marticus, so this is not data of my own. But it is there, it is available on the internet. If you Google loss given default, I think you will find this data set. Shobha, are session recordings from your classes? Shobha, you can contact Imarticus for that. So because they are it is saved on their systems. Okay. So I don't have it on my system, so I cannot share it. So you can better ask those guys. Okay, if you need our session recording. Yeah, Amrachi. So you can ask Imarticus about that. In R you had, yes, sometimes see the same data I can divide it into, see, we will also have multiple data sets tomorrow. So in tomorrow's case study we will see multiple data. So that is the same thing. So if you have two data sets, you don't have to split. You will just train the data on one and you will test it on the other data. So it's like they have splitted the data for you and they have given it to you. Okay, so you don't have to split it, they have already splitted and given the data to you. As simple as that. Okay. Okay, guys. So try to revise whatever was covered today, and if you have any doubts, we can take it up in tomorrow's class. Okay. I have to run because I have a class at 4, so I gotta quickly have my lunch and then take some rest. Okay, guys. Please, we must have your. Okay. Yeah, Amrachi, you can contact Imarticus for that. Okay. Okay. Bye, guys. Have a good Saturday. Okay, see you tomorrow. Bye. So I'm closing the Shamin, I will answer. Okay, Shamin, I will answer that tomorrow. Okay, just remind me once. Or you go through the video, you'll understand. I already spoke about it twice. Bye, guys. And tomorrow we are meeting at the same time, okay? It's 11 to 3.